Hello, my name is Todd. I'm going to be your tutor, your logic tutor today. We're continuing with our explanation of the rules of inference so that we can do natural deduction. We are on constructive dilemma now, which bears a striking resemblance to simple dilemma. Okay, let's suppose that we have P or Q. And if P, we get an S. But if Q, we get a T. Well, we know that we have the P or the Q, so we're going to get either an S or a T if we have the Q. So we can conclude S or T. So if these were premises, 1, 2, 3, we could say 4 we know to be true because of 1, 2, and 3 by constructive dilemma. Now remember that the shapes in our system are variables, so those shapes can represent simple statements, complex statements, negated statements, you name it, just so long as you have the instances, substitution instances of 1, 2, and 3, you may conclude the substitution instance of 4. So let me give you an example here. Suppose that we've got F or B if and only if Q, B if and only if Q, then Z, and F then R. Well, what could we conclude from these three facts? Well, we would get Z or R as 4 from 1, 2, and 3 from constructive dilemma. And just like all the other rules of inference, the order that the premises are found doesn't matter. So these could have been on different lines, 1, 2, and 3. Just so long as we had each of them, a substitution instance of them, we would be able to deduce 4. Okay, let's move on to our next one. Simplification. Suppose that we have P and Q. For example, I have burger and fries. Well, from that, it follows that I have a burger. So if we knew this, we could deduce P from 1 by simplification. Okay, and remember that these shapes up here represent variables, so long as we have a conjunction, we may simplify to the first or left conjunct, no matter what it is. So for example, suppose we have not, S or T, and Z. That's our premise. We may deduce not S or T from 1 by simplification. Okay, now, one thing you might be tempted to do, suppose we have P and Q, you might want to say Q from 1. Well, that is a valid move, but it's not allowed by our rule. Technically speaking, if you look up here, we are allowed to deduce the first conjunct and not the second. Yes, this is valid down here, but it's not allowed according to our rules. We will have a workaround later. It will go something like this. If we know that P and Q is true, we know that Q and P is true, and then by simplification we'll know that Q is true. Okay, let's move on to another. Here we have the rule of inference, conjunction. So suppose that we know that P is true and we know that Q is true. Well, then we know that P and Q is true. So those are our premises. This is 3. We'd say 3 is true by 1 and 2 by conjunction. Now, there's kind of an asymmetry here between simplification and conjunction. Because the order of the premises doesn't matter, if you have a substitution instance of 1 and a substitution instance of 2. You may put them together any way that you like. So the P could come first, followed by the Q, or you could have said Q, then P on line 3 from 1 and 2 by conjunction. Remember, the shapes represent variables, so here's another instance of conjunction. Let's say B if and only if M and not X. Well, from those, if they're premises, we could say B if and only if M and not X from 1 and 2 by conjunction. Let's move on to our next rule of inference. I think it's our final rule of inference, addition. Okay, suppose that we have some statement constant P. Well, what follows from that? Well, what follows is P or anything you want. Okay, now why should that be true? I could say P or S if and only if Z, then, we'll put this in brackets, R. I could say P or this whole thing, so long as I know that P is true. Well, why? Well, look up here to addition. Remember, these argument forms and the rules of inference we have based on them are saying that these arguments are valid. So if the box is true, well, box or anything, true or anything, is going to be true, and that would be a valid argument. That's why we can put anything we want as a second disjunct. Okay. That takes us through all of the rules of inference, and I want to just give you a quick example of what you'll be doing with them. Now, this is jumping in the deep end, as it were, but don't worry, we'll start out slow when we actually start doing these things. So on this problem, 1, 2, 3, and 4 are premises, and we have to prove, using our rules of inferences, that A or B follows. So the first thing I'm going to do is look for A or B, and I don't see it, but I do see that there is an A on line 2. So if I could isolate the A, I could add or B by addition, and I would be done. So I need to think, well, how can I get the A out of line 2? And I notice that line 2 is a disjunction. It says not J or A. So if I had a J, I could do a disjunctive syllogism. And I happen to look at line 4 and I see it says not C or J. So I could get a J from 4 if I could find the opposite of not C, which would be C, because then I could do a disjunctive syllogism. Well, I don't see a C, but there's actually one hiding up here in 1. It says not C, then F. Well, if I had a not F, by modus tollens, I could deduce a C. And fortunately, right there on line 3, I have a not F. So the first thing I would say is C comes from 1 and 3 by modus tollens. Okay. Now, why did I get the C? I got the C to get the J out of line 4. So look at 4 and 5 now. Not C or J, I've got the opposite of not C. So I can say J from 4 and 5, disjunctive syllogism. Okay. Why did I get the J? Well, I was after an A out of line 2. And so look, it says not J or A, and I've got the opposite of the not J, so I can do disjunctive syllogism and get A. And that would be, I use the lines 2 and 6, disjunctive syllogism. Now I'm close. Remember, I have to get to A or B, and I've got an A. So all I have to do is say A or B from 7 by addition. And we're done. All right, we'll continue this series with practice applying these